You ever look at a circuit diagram and it just looks like a bunch of weird lines and symbols? Well, don't worry. By the end of this, you're going to be able to read that language like a pro. We're going to break down all the essential parts that make everything work, from a simple flashlight to the smart gadgets in your home.
So here's how we're going to do it. We're going to build a circuit right from the ground up. We'll start with the absolute must-haves. Then we'll figure out how to control the electricity, how to measure what's going on, and then we'll get to the really fun stuff, the smart components that can actually react to the world around them.
Okay, let's just dive right in. Every single circuit, and I mean every circuit, no matter how complicated, needs two basic things to even exist. It needs a source of power to get things moving, and it needs something for that power to actually do.
First up, the heart of the circuit, a cell or a battery. This is what provides the voltage. You can think of it like the electrical push that gets everything started. Without a power source, nothing happens. You just have a collection of parts that won't do a thing.
And now our power has a purpose. A classic filament lamp is a great example of an output. When the electricity flows through that little wire inside, it heats up, it glows, and boom, you have light. And just like that, with just a battery and a bulb, we've made the simplest, most fundamental circuit you can imagine.
So a circuit that's just on all the time isn't super useful, is it? Or very safe for that matter. So the next logical step is to add some parts that let us manage and direct that flow of electricity.
This is our most basic form of control. You close the switch, you complete the path, and electricity flows. Open it up, you create a gap in the path, and everything turns off. It's literally the same thing as the light switch on your wall. Simple, but absolutely essential. Now, think of a fuse as a little bodyguard for your circuit. It's a one-time use safety device. See, inside there's a tiny wire that can only handle so much current. If there's a sudden power surge, that wire instantly melts, breaking the circuit. It sacrifices itself to protect all the other more expensive components from getting fried. A diode is basically a one-way street for electricity. It's like a bouncer at a club. Current can flow through it easily in one direction, but if it tries to go backward, nope. It gets completely blocked. This is so important for protecting sensitive electronics that could get wrecked by reverse current.
Okay, now this is where things get really clever. An LED, or light-emitting diode, does two jobs at once. It's a one-way street, just like a regular diode, but, and this is the cool part, it has this awesome side effect of lighting up whenever current is flowing through it the right way.
And because they are so incredibly efficient and last forever, LEDs are just everywhere now. The glowing numbers on your alarm clock, those super bright traffic lights, the new bulbs in your house. Once you know what they are, I promise you will start seeing them all over the place.
All right, our little circuit is getting more sophisticated. We can power it, we can control it, but how do we know what's actually happening inside those wires? I mean, you can't see electricity. So to do that, we need some specialized tools. Meet the two most important gauges for any circuit. An ammeter measures current, which is the actual flow of electrons. So, to measure that flow, you have to break the circuit and stick the ammeter right in the middle of the path, in series, so all the current has to run through it. A voltmeter, on the other hand, measures potential difference, which is more like the electrical pressure. To measure that, you connect it in parallel, one probe on either side of a component to see the difference in pressure between the in and the out. Okay, now let's talk about something that exists in all circuits, resistance. You can pretty much think of it as electrical friction, and we use special components called resistors to very precisely control just how much current is flowing. This is your standard no-frills workhorse resistor. It has one job: provide a very specific, unchanging amount of resistance. Let's say you have a tiny LED that can't handle a lot of current. Well, you put a fixed resistor right in front of it to slow that current down to a safe and predictable level. But what if you don't want a fixed amount of resistance? What if you want to be in control? Well, that's where the variable resistor comes in. By turning a knob or sliding a switch, you can change how much resistance it provides. This is exactly what's inside a dimmer switch for a light or a volume knob on a stereo. All right, this is where circuit design gets really, really cool. We're moving on to components that are more than just passive parts. These are smart resistors that can actually sense what's happening in the world around them and react to it. So meet the light-dependent resistor, or LDR for short. This little component's resistance completely changes depending on how much light is hitting it. This simple ability to see lets a circuit make decisions all on its own, based on whether it's bright or dark outside. Now you gotta look closely at this table, because this is the secret. It works in a way that's kind of the opposite of what you might expect. When it's super bright, its resistance drops to almost nothing, which lets a lot of current flow through. But when you put it in the dark, its resistance shoots way, way up and basically blocks the current. This simple behavior is the key to so many automated gadgets.
And that simple trick, low resistance in light, high resistance in dark, is how all sorts of automated things work. It's how a street lamp knows when to turn on at sunset. It's how an automatic nightlight works. It's even how a burglar alarm can be set off by the beam of a flashlight.
A thermistor works on a really similar idea to the LDR, but instead of sensing light, it senses heat. It allows a circuit to measure and react to changes in the temperature of its environment. And if you look at the table, you'll see a very familiar pattern. It's that same inverse relationship. When things get hot, the resistance goes low. When it gets cold, the resistance climbs way up. And it's this predictable change that lets a circuit basically read the temperature. And this property makes thermistors absolutely perfect for any device that needs to keep an eye on temperature. We're talking digital thermometers, the thermostat that controls the heat in your house, and even the critical sensor that keeps a car engine from overheating. And that's pretty much it. From the simple push of a battery to a tiny sensor that can feel heat, you now get the basic building blocks of all electronics. Every complex device you can think of is just made by combining these simple parts in really clever ways. So the real question is, now that you have the toolkit, what would you build?